Legendre polynomials. In physical science and mathematics, Legendre polynomials, named after Adrien-Marie Legendre, who discovered them in 1782, are a system of complete and orthogonal polynomials with a vast number of mathematical properties and numerous applications. They can be defined in many ways, and the various definitions highlight different aspects as well as suggest generalizations and connections to different mathematical structures and physical and numerical applications. Closely related to the Legendre polynomials are associated Legendre polynomials, Legendre functions of the second kind, and associated Legendre functions. Definition by construction as an orthogonal system. Definition by a generating function. Definition by a differential equation. Orthogonality and completeness. Rodrigues formula and other explicit formulas. An especially compact expression for the Legendre polynomials is given by Rodrigues formula. This formula enables derivation of a large number of properties of the Pn \Pn s. Among these are explicit representations such as in the third representation, n/2 stands for the largest integer less than or equal to n/2. The last representation, which is also immediate from the recursion formula, expresses the Legendre polynomials by simple monomials and involves the generalized form of the binomial coefficient. The first few Legendre polynomials are. The graphs of these polynomials up to n equals 5 are shown below. Applications of Legendre polynomials. Expanding a 1/ or potential. The Legendre polynomials were first introduced in 1782 by Adrien-Marie Legendre as the coefficients in the expansion of the Newtonian potential, where r and r are the lengths of the vectors x and x respectively, and g is the angle between those two vectors. The series converges when the expression gives the gravitational potential associated to a point mass, or the Coulomb potential associated to a point charge. The expansion using Legendre polynomials might be useful, for instance, when integrating this expression over a continuous mass or charge distribution. Legendre polynomials occur in the solution of Laplace's equation of the static potential, 2px equals 0 in a charge-free region of space, using the method of separation of variables, where the boundary conditions have axial symmetry, no dependence on an azimuthal angle, where z is the axis of symmetry and th is the angle between the position of the observer and the z-axis, the zenith angle. The solution for the potential will be L and BL are to be determined according to the boundary condition of each problem. They also appear when solving the Schrödinger equation in 3 dimensions for a central force. Legendre polynomials and multipole expansions. Legendre polynomials are also useful in expanding functions of the form this is the same as before, written a little differently, which arise naturally in multipole expansions. The left-hand side of the equation is the generating function for the Legendre polynomials. As an example, the electric potential PHRTH in spherical coordinates due to a point charge located on the z-axis at z equals a C diagram right varies as if the radius r of the observation point P is greater than a, the potential may be expanded in the Legendre polynomials, where we have defined E equals a/r1 and x equals cos th. This expansion is used to develop the normal multipole expansion. Conversely, if the radius r of the observation point P is smaller than a, the potential may still be expanded in the Legendre polynomials as above, but with and are exchanged. This expansion is the basis of interior multipole expansion. Legendre polynomials in trigonometry. The trigonometric functions cos nth, also denoted as the Chebyshev polynomials t and cos th, cos nth, can also be multipole expanded by the Legendre polynomials p and cos th. The first several orders are as follows. Another property is the expression for sin n plus 1th, which is 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 which Legendre polynomials in recurrent neural networks. Additional properties of Legendre polynomials. Recurrence relations. As discussed above, the Legendre polynomials obey the three-term recurrence relation known as Bonnet's recursion formula, and or with the alternative expression, which also holds at the endpoints. Useful for the integration of Legendre polynomials is. From the above one can see also that, or equivalently, where Pn is the norm over the interval 1 equals x equals 1, asymptotics, zeros, pointwise evaluations, the parity and normalization implicate the values at the boundaries x equals plus 1 backslash display style x equals backslash pm1 to be at the origin x equals 0 backslash display style x equals 0. One can show that the values are given by Legendre polynomials with transformed argument. Shifted Legendre polynomials. The shifted Legendre polynomials are defined as here the shifting function x2x1 is an affine transformation that bijectively maps the interval 0, 1 to the interval 1, 1, implying that the polynomials p and x are orthogonal on 0, 1. An explicit expression for the shifted Legendre polynomials is given by the analog of Rodrigues' formula for the shifted Legendre polynomials is the first few shifted Legendre polynomials are Legendre rational functions. The Legendre rational functions are a sequence of orthogonal functions on 0, the row, the 0, 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 the 0. They are obtained by composing the Cayley transform with Legendre polynomials. A rational Legendre function of degree n is defined as they are eigenfunctions of the singular Sturm-Liouville problem with eigenvalues